Let's change gear a bit to know more about the science of programming. There are many ways of achieving an answer with different programs, different brands of computers. You can take timing in one computer, but this is going to be different in another computer. So what basis we can use to know what is good versus what is bad program or algorithm? This video is to answer this question in some way with order of growth. First, there is actually a difference in the so-called algorithm versus program. Algorithm is in general referring to some understandable way of solving a problem. Some of the specific is not detailed inside an algorithm. On the other hand, a program is a realization of an algorithm to solve the problem in some programming language. For us, we usually use them interchangeably. We write program is to get problem solved fast to a computer. We definitely want to run the program and complete it as short a time as possible. So time is a consideration. There is a less obvious consideration too. It is space. Memory usage to the computational problem. Why? In fact, if you do not consider the space, that is, you have unlimited amount of space, one can pre-compute all the answers to the problem. Each time when you have an input, the so-called program can just look up the answer in a very fast time. So computation is always fast. This is not practical in the algorithmic world. Well, you may now know that there could be a trade-off of time and space. This is the study in some advanced topics of computer science. So we are interested in the time and space. Time, how long it takes to run a program. Space, how much memory it needs to run. But then there are many different kinds of computers. So which computers are we talking about the time? Also, there are various possible inputs to handle. What time or space are we talking about? To be objective, we talk with no specific computers, but growth rate with reference to the size of input. Again, talking about absolute numbers is not very meaningful, so we talk about order of growth with respect to the size of input. We want to ask questions like this. When we do factorial 5 versus factorial 10, that is when we double the number, what is the kind of increase in time and space we need? Or when we do Fibonacci 10 versus Fibonacci 20, here we also double the number, what is the kind of increase in times and space we need? That is, what is the trend of growth in the time and space with respect to size? Is it 2 times, or the same, or 4 times, or what? So we are interested in the order of growth with respect to size. We write this as a function of size. Formally, we have n denote the size of the problem. For example, you have Fibonacci 5, then n is 5. Fibonacci 10, then n is 10. Let Rn denote the resources needed. Resources here refer to the time and the space. Then we say Rn has order of growth theta Fn if they are positive constant k1 and k2 such that Rn is bounded below by Fn times k1 and bounded above by Fn times k2 for any sufficiently large n. That means this condition needs to be fulfilled only for n sufficiently large. When n is small, this may not be true, but that is okay, as you will see in the next slide. Then we write Rn equal to theta Fn. Here is a figure to show what we talked about in the last slide. Y-axis is the amount of resources needed. X-axis is the size of the input. Here's a sketch of Rn, K1Fn, K2Fn. This is just a sketch to show the various functions. More realistically, all these functions should be increasing function in the size of the input. Anyhow, we show the function here to indicate that we don't care when n is small. Instead, we are interested in the scenario when n is larger than some number n0 here. In this case, Rn is sandwiched between the two functions. Rn is upper bounded by this function, so we call this big O Fn. And Rn is lower bounded by this function, we call this omega Fn. So if these two conditions are fulfilled, it means that this inequality is fulfilled for n larger than some n0, the order of growth of Rn is Fn. We write Rn equal to theta Fn. In this course, we generally only worry about upper bound, On. That means we only have this part of the inequality. There are freedoms in the choices of K1 and K2. A choice of K1 and K2 will affect the number N0 to be smaller or larger, but Rn of some particular order of growth will remain so for the different choices of K1 and K2. Also, for using a better computer or a slightly different implementation of an algorithm, Rn for time or space may be lower than the curve here. Still, the flexibility of choosing K1 and K2 is to allow us to still bound Rn for Rn coming from constant difference in the use of resources among the various kinds of computers. That is, the order of growth Rn of a program doesn't change even if we change to a better computer or a slightly different implementation of the algorithm. Some common examples of Fn: constant, n, n squared, n cubed, log n log n, 2 to the power of n. We can put all these functions in the axis of increasing non-practicality. That means put them to see how practical things are. Constants, of course, you take only a constant amount of time or space. This is the best scenario that we can have. Followed by log n and n. Log n is smaller than n because log n grow much slowly than the n. And n log n, which is the product of these two, of course, it's bigger than n because log n is larger than 1. Followed by n squared, then n cubed, then 2 to the power of n. On the whole, we have constant, logarithmic, linear, n log n, quadratic, cubic, and exponential in the order of increasing non-practicality. In practice, we would like to have programs running within this range till about cubic. Anything beyond are considered not so practical. In particular, exponential is not practical at all.
Let's see the recursive factorial in lecture 2. We know that time is proportional to the number of operations we do in the whole process. We analyzed in lecture 2 that the number of operations is actually linearly proportional to n. It is about 2n. So this is order of n. What about the space? The space is proportional to the number of pending operations. And in lecture 2, we saw that the number of pending operations is also linearly proportional to n. In particular, we need to keep track of all the multiplications and the numbers that need to go with the multiplication. So this is also O of n. Let's compare it with the iterative process that we saw in this lecture. We have this factorial with the while loop and this factorial with the for loop. In both cases, we saw that the time, which is proportional to the number of operations, is also linearly proportional to n. And so this is O of n, which is the same as that for the recursion version. On the other hand, the space is constant. As we analyze it, we only needed the constant number of variables to do all the operations, and we do not have any defer operation. So this is O of 1, constant, which is much better than that for the recursion. These two other versions of the codes are also the same. The time is linearly proportional to n, so it's On, which is the same as that for the recursion. And the space is constant because there are only constant number of variables to keep track of. And so it is O of 1. This is also better than the recursion version. Here's a table to sum up all our examples and our recursive versions and our iterative version. We have just seen factorial. The time is On, space is On in the recursive solutions. On the other hand, for its iterative solutions, we have the time is the same, O of n, but the space has improved from O of n to O of 1. Next, Fibonacci n. In the recursive one, it repeatedly calculates some Fibonacci numbers. As you can examine the recursion tree, the time is exponential as a result. On the other hand, the space is linear because this is the depth of the recursion tree. For the iterative solutions, we simply do one Fibonacci number at a time from the previous two Fibonacci numbers. This resulted in a vast improvement to needing only linear time. The space is also reduced to just keeping track of the last two Fibonacci numbers, and thus is a constant. Next, GCD A and B. The time is O of A or B, depending on who is larger. Actually, the number of iteration is capped at B, as we saw, if we assume B is smaller than A. The space is also O of max A, B, because the number of times that we have to call the recursions is the number of items that we put on the stack. As for the iterative solutions, the times remains the same as that for the recursive solutions. On the other hand, because we simply calculate iteratively, we do not put things on the stack. We just simply calculate R as needed, and the space requirement is constant. Towers of Hanoi with n disks. The time is exponential in n, as you can explore the recursion tree to see that this is indeed exponential in n. And the space is O of n, which is the depth of the tree. And for this case, I did not give you any iterative solutions, as I reckon this is hard to do. I will not try it. Changing of coins of amount A and n number of coins. This is exponential in A, assuming n is a small number. Again, the space is the depth of the recursion tree. The order is A plus n if we include n in here. This is the third exponential recursion we saw. The first one was the Fibonacci, which we managed to do some improvement with the iterative solutions. The second is the Towers of Hanoi. We didn't give you any iterative solutions. Here, this is the third case where we actually have a good solutions for it with time A times n and space also A times n. Compare this with this, you see that the space is now larger than A plus n in the recursion solutions, but the time has vastly improved from exponential to just multiplications of two numbers, which is quadratic. You can see that this is also a form of trading the space for time. That is, we now use more space, but we have reduced the time from exponential to just quadratic.
In the previous few slides, we actually have computation that took some constant times n, the size of the input, plus minus some number of steps to complete the calculations. And we took the order of growth to be linear. This is because O of 2n plus 1, for example, is the same as order of 2n, and order of 2n is the same as order of n. In this simplification, we actually drop the smaller term. Between 2n and 1, 2n is larger, so 1 is dropped. And then in 2n, the constant here is dropped to give us order of n. On the whole, we took the larger term and dropped the constants along the way. How about 3n plus 4n squared plus 4 steps? What is the order of growth? The order of growth is equal to O, just take the whole thing, and we see that 4n squared dominate 4, so 4 can be dropped. On the other hand, 3 to the power of n dominate 4n squared, so this is dropped. As a result, we have O of 3 to the power of n, exponential. This part of the material is in the so-called analysis of algorithms, such as CS1010X, CS3230. For our purpose here, we have a few tips that we use often to put out the order of some functions. First, we identify dominant term. Ignore smaller terms. Second, we ignore additive or multiplicative constants. Here is an example. 4n squared minus 1000n plus 300,000. This is order of n squared because the dominant term is 4n squared and the constant 4 is dropped, so we are left with n squared. N divided by 7 plus 200n log n. It's in the order of n log n because n log n is larger than n divided by 7 after some fixed large enough n. So this is the dominant term. 200 as a multiplicative constant is dropped. So we are left with n log n. Note that we often work with logarithmic. Log b to the base a is the same as log b to the base c divided by log a to the base c, and this is a constant. So in the order of growth, order of log b to the base a is no difference from order of log b to the base c, and we often write it simply as order of log b with the assumptions of base 2. Here is what we will usually do to get the order of growth. By counting the number of basic computational steps. We try a few small values of n to understand the flow of the program, and then we extrapolate for really large n, look for worst case scenario to count the basic computational steps. Here is our common functions again. Let's take a look at their numerical values. N is 1, log n is 0, n log n is 0, n squared is 1, n cubed is 1, to the power of n is 2. N is 10, you have 2.3 for log n, 23, and so on. When n is large, 10 to the power of 6, log n is still pretty small. N log n is getting large, n squared and n cubed get larger, and 2 to the power n become impossible. you see that log n grows pretty slowly, n log n is pretty decent still, n squared it's getting pretty fast growth, n cubed it's even worse, and to the power n it's really huge and no longer practical. We show you the numerical table in the previous slide is to remind us that some solution we may have does work in theory but may not be practical at all if it falls under the region of n cubed or larger. The moral of the story is that there are different ways of performing a computation, and these different ways can consume dramatically different amounts of resources in terms of times and space. So we have to be very careful at time. For this course, we generally may not always need to know the best solutions to a problem, but we should be mindful of possible better solution in many cases. More about such a topic on algorithm designs is left to later courses in the school. Let's look at one example to see different ways of solving a problem to get a better time and space requirements. Here the problem is b to the power of e that we want to compute. Define power b to the power of e, that's what we want to compute. Define power product, this is a helper functions. With b and e the same as here, the a is there to accumulate the answer. So this is a helper function for us to call with power product 1, b, e. 1 is the a is to accumulate the answer along the way into the recursion. So a is what we call the baggage before that brought into the recursion till the very end, and a is the answer. Each time when the recursion call, the answer is accumulated in a starting with a equal to 1, and each time the power is reduced by 1 till the power equal to 0. We have completed the calculations of a equal to b to the power of e. So what is the time requirement here? The depth of the recursion is e because we need to call this helper function e times. Each time we reduce by 1. And each time in the recursion it does constant amount of work. So in total the time requirement is O of e. What about the space requirement? We actually stack up O of e recursive calls to get the answer. So the space requirement is also O of e. We take the e here as the input size, equivalent to what we usually see as n. Can we do better? Yes. Here is how we do it. By looking at an alternative definition of b to the power of e as equal to 1 when e equal to 0, and when e is even, we can take the b square and half the exponent. If e is odd, then we take the b out and left behind e minus 1, that will be even. So we have b to the power of e minus 1 times b. With this, we can have the fast exponentiation done as follow. Define fast exponent b to the power of e. If e equal to 0, return 1 as according to the definition. Else if e is an even number, we return fast exponent according to the definition. The exponent to be b squared times half the exponent. Else you take out the b and do the fast exponent with b comma e minus 1, which is going to be an even number. So the time complexity or the time requirement, in this case it's O of log e. What about the space requirement? This is also O of log e. Why? You can think about it. We can discuss this in recitation. Can we do this iteratively? Yeah, I shall leave this to you to try it out. To sum up this lecture, we have learned recursion and iteration. In recursion, we solve for a simple base case and we express the problem in a few smaller similar problems, and at times we bring along a baggage into the recursion. In iterations, we do while for loops to solve the problem. Now, in general, an iterative process is usually more efficient than a recursive one, but sometimes it is hard to devise an iterative solutions, whereas a recursive one is straightforward and more elegant. We also learned order of growth for time and space, and we noted different algorithms can consume dramatically different amount of resources, and we should pay attention to efficiency. Let's take a quick stock on what we have learned over the past weeks. We learned to write function or algorithm. In fact, if you take a recipe from the web, you can see some similarity between a function and a recipe in making a dish. It can be concise with similarly the following 3 kinds of construct in the program. We have a sequence from top to bottom and left to right step by step. And we have conditioner to allow branching to do differently depending on the situation. We need a looping to allow repetition to do until certain conditions are met. This is realized with while loop or recursions of calling itself. Then we learned about the way to talk about whether a program is good or bad with the order of growth, rather than absolute timing that can be quite different for different computers. All in all, computer science is algorithm plus data structures. So you have seen algorithm very much. Data structure is ways of organizing data in computer to facilitate computation. Alright, so data structure is in a supporting role to help algorithm in performing the task efficiently. For example, we will be learning string, set, tuple, list, dictionary to help us in writing good algorithm. Before going into data structure abstractions, we have more functional abstraction in lecture 6.